Hi all, this is Bharatraj. I am studying BTech first year CSC A section. My roll number is 21951A0522. Today my concept video is Lagrange's theorem. Lagrange's theorem is one of the central theorem of abstract algebra. It states that in group theory, for any finite group, say G, the order of group subgroup H of group G divides the order of G. The order of group represents the number of elements. This theorem was given by Joseph Louis Lagrange. Let us discuss the statement and proof of Lagrange's theorem, and also let us have a look at the three lemmas used to prove this theorem with the examples. Now, Lagrange's theorem statement. As per the statement, the order of the subgroup H divides the order of the group G. This can be represented as delta G equal to delta H. Before proving the Lagrange's theorem, let us discuss the important terminologies and three lemmas that help to improve this theorem. First of all, what is coset? In group theory, if G is a finite group and H is a subgroup of G, if G is an element of G, then GH equal to H an element of H is a left coset of H in G with respect to the element of G, and Hg equal to small h an element of capital H is a right coset of H in G with respect to the element of G. Now let us have a discussion about lemmas that helps to prove Lagrange's theorem. There is a Lagrange's theorem statement. Now there are three lemmas. Lemma 1, lemma 1. If G is a group with subgroup H, then there is a one-to-one correspondence between H and any coset of H. Lemma 2 says that if G is a group with subgroup H, then the left coset relation G1 is symmetric G2 if and only if G1 into H equal to G2 into H is an equivalence relationship. Lemma 3 says that let S and S be a set and be an equivalence relationship on S if A and B are two equivalent classes with A intersection B equal to pi, then A equal to B. Now, Lagrange's theorem proof. Let H be any subgroup of the order n of a finite group G of a order m. Let us consider the cost breakdown of G related to H. Now, let us consider each coset of H compressing n different elements. Let H equal to H1, H2, H3, H4 and so on till Hn. Then AH1, AH1, H2, H3, so on till AHn are the n distant members of AH. Suppose AHI equal to AHJ, then HI equal to HJ with the concatenation law of G. Since G is a finite group, the number of discrete left cosets will also be finite, say P. So the total number of elements of all coset in NP, which is equal to the number of total number of elements in G. Therefore, hence M equal to NP and P equal to M by N. This shows that in the order of H is a divisor of M, the order of the finite group G. We also see that the index P is also a divisor of the order of group. Hence proved, that is delta G equal to delta H. Now application of Lagrange's theorem. A sequence of a theorem is the order of any element order A of a finite group, that is the smallest positive integer number k with a power k equal to e, where e is a identity element of the group. Devise the order of the group since the order of A equal to the order of the cyclic subgroup generated by A. If the group has n elements, it follows A power n equal to E. If group has n elements, okay, sorry, this can be used to prove Fermat's little theorem, and it generalization eludes theorems. This special case were known long before the general theorem was proved. The theorem also shows that any group of prime order is cyclic and simple. This is in turn can be used to prove Williamson theorem, that is P is prime and then phi factor of A is P minus 1. Now, extents of subgroup of given order. Lagrange's theorem raises the converse questions as to whether every divisor of the order of a group is the order of some subgroup. This does not hold in general given a finite group G and a divisor of D of delta G. That does not necessarily exist as a group subgroup of G with the order D. The smallest example is A4, the alternate group of degree 4, which has 12 elements but no subgroup of order 6. A converse of Lagrange's theorem, that is CLD group, is a finite group with the property that for every divisor of the order of the group, there is a subgroup of the order. This is known that CLT group must be soluble, and that every super soluble group is a CLT group. However, there exist soluble groups that are not CIT, for example, A4, and CIT groups that are not super soluble, for example, S4, S4, the symmetric group of degree 4. There are partial convergences of Lagrange's theorem. For general groups, Cauchy's theorem unites the extension of an element and hence a cyclic subgroup of order any prime dividing the group order. Cauchy's theorem extends this to the extension of a subgroup of order equal to maximal power of any prime dividing the group order. For soluble groups, Hall's theorem asserts the extension of a subgroup of order equal to any unitary divisor of the subgroup, that is a divisor co-prime to its cofactor. Now, counterexample of converser of Lagrange's theorem. The converse of Lagrange's theorem states that if D is a divisor of the order of a group G, then there exists subgroup H where delta H equal to D. We will examine the alternate group A4, the set of given permutations as the subgroup of the symmetric group S4. That is A4 equal to, we taken some example A comma 1 2 of 3 4 and 1 3 2 4 1 4 2 3 1 2 3 1 3 2 1 2 4 comma 1 4 2 comma 1 3 4 comma 1 4 3 comma 2 3 4 comma 243. Therefore, a delta 4 equal to 12. So the divisor of 12 is 1 2 3 4 6 12. Assume to the contract that there exists a subgroup H in A4 with the delta H equal to 6. Let V be the non-cyclic subgroup of A4 called the Kalin 4 group. Therefore, V equal to E comma 12 34 comma 1 3 24 comma 1 4 2 3. Therefore, let K equal to H intersection V. Since both H and V are subgroups of A4, K is also a subgroup of A4. Now, for Lagrange's theorem, the order of K must divide both 6 and 4. The order of H and V representatively. The only two positive integers that divide both 6 and 4 are 1 and 2. So, delta K equal to 1 or 2. Let us assume first take delta K equal to 1, then K equal to E. If H does not share any elements with V, then the element in which beside the identity element E must be of the form of ABC where A comma B comma C are dissonant elements in 1, 2, 3, 4. Since any element of form ABC squared A ABCD and ABC of ABCD equal to E. Any element of H in the form of ABC must be paired with its inverse. The remaining 5 elements of H must come from distant pair of elements in A4 that are not in V. This is impossible since pair of elements must be even and cannot total up to 5 elements. The assumption that k equal to 1 is wrong. Our assumption wrong. So let we take the delta k equal to 2. Now delta then k equal to become e comma v, where v is belongs to v. So small v belongs to capital V. Small v must be in the form of A, B, C, D, where A, B, C, D are distant elements of 1, 2, 3, 4. The order of 4 elements in H are cyclic of length 3. Since there are only 2 distant posets generated by H, then H be normal. Because of that, H equal to G inverse, there G belongs to A4. In particular, In particular, this is true for G equal to ABC belongs to A4, since H equal to GHG inverse comma GVG inverse belongs to H. Without loss of generality, assume that A equal to 1, B equal to 2, and C equal to 3, and D equal to 4. Then G become 1 into 2 into 3, comma, V equal to 1 into 2 into 3 into 4, and G inverse equal to 1 into 3 into 2, and GV become 1, 3, 4, and GVG inverse become 1, 4, 2, 3. The transforming back, we get GVG inverse equal to A into B into V into C, because V contains all disjoint transpositions in A4. Then G into V into G inverse belongs to capital V. Hence, G into V into G inverse belongs to H intersection V equal to K. Since G into V into G inverse not equal to V, we have demonstrated that there is a third element in K. But earlierly, we assumed that delta K equal to 2. So, det K equal to 2. So, we have a contradiction. Therefore, our original assumption that there is a subgroup of 6 is not true, and consolidating there is a no subgroup of order 6 in A4, and the consider of Lagrange's theorem is not necessarily true. Now, history of Lagrange's theorem. Lagrange himself did not prove the theorem in general form. He started in articles, reflections, Schur law, resolution, algebraical design equations, that if a polynomial in n variable has its variables permitted in all n not equal ways, the number of different polynomials that are obtained is always a factor of n. For example, if the variable x, y, and z are permitted in all 6 possible ways in the polynomial, that is 6 plus y, sorry, x plus y minus z, then we get a total of 3 different polynomials. They are x plus x plus y minus z, and x plus z minus y, and y plus z minus x. Note that 3 factors. Note that 3 is a factor of 6. Oh, the number of such polynomials is the index in symmetric group Sn of the subgroup of H. Permission that preserve the polynomial. For example of x plus y minus j z, the subgroup H is in a S3 contain the identity and the transposition. So the size of H divides in with the later development of abstract group. This result of Lagrange's polynomial was recognized to extend to the general theorem about finite group, which now bears its name. Here we prove that Lagrange's theorem statement that det G equal to det H. This is the history of Lagrange's theorem. And this is my concept video Lagrange's theorem. Thank you.